Yes. Yeah, our pleasure to invited Shiwei Zhang from CCQ Flatiron Institute to continue to introduce about the Monte Carlo beyond the cyclography systems. And yes, please.
Thank you. So, thank you. We're gonna pick up. So yesterday we talked about trying to control the sign problem in the finite temperature framework, understanding the problem, and then understanding exact conditions as limiting cases of how to control the sign problem, and then implement constraint path approximation with finite temperature. So we're going to pick this up, and then I'm going to move to ground state, talk about constraint path in that framework, and then phaseless. Unfortunately, the naming was my fault. So the early work was actually ground state. It came to be known as constraint path Monte Carlo. And then this has a phase problem. There's a fundamental subtlety that took many years, multiple years, to figure out that had to do with a phase projection. So we called it phase-free, I think, actually, in the first paper. But it's come to be known in sort of chemistry as phaseless AFQMC. It's view, phaseless as the generalization of constraint path, and then the reverse direction goes phaseless. If you don't have a complex phase, it'll collapse back to constraint path. I wasn't quite. I decided for today to go away from lattice models and talk about real materials, even though I think that's a little bit further from your interest. But I thought so that's a downside. I wanted to. We have a lot of work in correlated models. I'd love to share with you. But I thought the advantage would be that this exposes a bigger aspect of the algorithms, and so I'll maybe make a coupling with what you already seen and reinforce what we talked about yesterday to gain a little bit more intuition. So that's what I decided to do, and I'm happy to talk to you about models more. So we're gonna basically try to use this to explain the ground state algorithm a little bit more so you get a better feel, and then just give you very quickly a few examples in ab initio calculations in solids and quantum chemistry. We talked about how we should have a mindset or paradigm shift from sort of our traditional way to think about QMC in condensed matter theory or lattice gauge theory, which is to stay with the sign problem free exact calculations, but rather we give up on one-shot exactness because for materials, as you quickly see, it's very difficult to make progress if you don't get that help, and try to control the sign problem, and then improve the approximation through different channels. For example, we mentioned a little bit about self-consistency. So the obstacles for going to real materials, there are several fold. One is there's long-range interaction. So one way to connect with what you've seen is that you could think about a simulation of real materials as some generalized lattice, and this is not necessarily 2D and doesn't have to map. You can have a three-dimensional lattice or molecule, but you can always think about, and I'll explain how this comes about, some sort of a lattice. And then you have a one-body term that's general, that involves hopping from one side to the other, could be from anywhere to anywhere. And then the interaction is a four operator process, right? Scattering involving four sites like that. So I, J, K, L. And the matrix elements can be obtained. So naively, this has difficulty because in order to decouple this Hubbard-Stratonovich, you would need order m to the fourth power type of fields. You handle order m to the fourth power matrix elements, and you need that many fields, a lot of fields. The sign problem turns into a phase problem. I'll show you. So just to remind you how those matrix elements come about, the electronic Hamiltonian can be thought of as one-body and two-body terms. In first quantization, you have kinetic energy. So I mentioned that you could think about a hydrogen chain. So the protons are fixed, and the electrons move about. So this is a Hamiltonian about the electrons. So their kinetic energy, they experience an external potential that comes from the nuclei being fixed, and then they interact. This is this red term. We can always use a single particle basis. For example, in chemistry, people like to use Gaussians that are centered on atoms, Gaussians of different width, and the chemists have meticulous basis sets that you can look up on a web and dial down. You know, if you have a silicon, you dial down a set of basis sets. Once you have these basis sets, you could evaluate, for example, this VIJKL that I just said as these basis indices. We said it involves 4 sites, right? So 4 indices of bases, and then you compute this Coulomb interaction that gives you the 4-index object. So the concept of a Slater determinant, we're gonna, this is a little bit different from the determinant that we were writing yesterday here, determinant of 1 plus b. This rather is a mean field solution to this problem. So in the Hubbard model, each column is the size of the lattice, and the number of columns is the number of electrons of a particular spin. So for example, upspin this many, and then there's a separate determinant for downspins.
The screen that we're seeing here is not the one being shared on Zoom. On Zoom, it's stuck on the floor on the first slide.
Oh.
The sharing.
So stop sharing. And try again. How's it now? Good? Okay. So I don't know where we lost it on Zoom. If there's a problem, please shout out, people on Zoom. I'm gonna try to continue. So we talked about how we obtain these matrix elements. And of course, the Tij, the one-body matrix elements, similar way, the kinetic energy can be evaluated with respect to 2 basis functions and the external potential as well. So the concept of a Slater determinant in the Hubbard model is just the orbitals written out as a function of sites. And here it's electronic orbitals written out in terms of the basis functions. So for example, this hydrogen chain, I've extended it. One orbital could look something like that. You know, actually, the simplest orbital would be the electron in a block state. That's equal distribution. So that's one red orbital. And the size of this orbital is the number of basis functions. So that doesn't have to be equal to the number of atoms anymore. In fact, that would be a minimal representation. Each atom would correspond to 10 basis functions, 20. So it would be 20 times the number of atoms. That many would be the size of a column. And we have depicted 2 columns here. So corresponding to kind of 2 orbitals. I'm trying to do that to show it's a p orbital or something. It has a sign, right? And you go on, you accommodate all your electrons. So that's a Slater determinant. Of course, we know very well how to manipulate this object. This concept will be important coming up next. So for each Slater determinant, it's a wave function that's an independent electron wave function that describes the system. It has an advantage in that it automatically already imposes Fermion antisymmetry, right? So a mean field solution is correct in terms of Fermion antisymmetry. So how do you write the Hubbard-Stoyanovich decomposition? So this is from this first paper that dealt with the phase problem. So it's written in plane wave basis or in terms of momentum space. So in a solid, periodic solid, this is routinely done in density functional immaterial simulations. If you have a periodic system, I've just showed you a simple incorrect depiction of M and O, the solid. So you have Mn and O in a cell, and you have these electrons. So the Hamiltonian has, as we said before, the electron Hamiltonian under the Born-Oppenheimer approximation has kinetic energy. and then what they experience from these. And in solid state, you could take out some core electrons. Like if you have a manganese, the neon core 1s, 2s, 2p electrons effectively create just an external potential. You can integrate them out. So that's what this electron ion thing is. It's like a pseudopotential the electrons feel. And then the electron-electron interaction, and then because of periodic boundary conditions, there's some background. So in a plane wave basis, you can write these out. These are called pseudopotentials. These are also engineered very carefully for you. And in plane wave basis, you can see that the local interaction has a G minus G prime form, as in local in coordinate space. The electron-electron interaction has this form 1/q² in 3D in Fourier space. And then you could decompose these by writing this in terms of momentum space as the momentum transfer amount, which translates into local in real space as a local density. So this is how you decouple it, and the number of fields becomes order linear in the size of the basis. And I think this has been recently sort of used again in the context of twisted bilayer graphene. But this is how we did the plane wave calculation. So for general chemistry thing, this VIJKL, you can use what's known as a Kolesky decomposition to factorize this VIJKL. So you don't have to diagonalize. If you diagonalize it, it's into the 6th power. You have to figure out how to decompose it. But this is into the 3rd cost. You could write this and then truncate. Jmax, Jmax would correspond to the number of fields you need, is typically 4 times 8, 4 to 8, on the order of 10 basis functions, right? So it's linear in the size of the basis, and that's important. It's like in the Hubbard model, which is linear in the size of the basis, right? It's when you do the Hirsch decomposition, it's equal to the size of the lattice. But here, for any general Coulomb interaction, it's still linear, has a prefactor. Okay, so now to summarize those 2 pages, you think about this general matrix VIJKL through a tensor decomposition into this form of two index things tied together by a tensor. This tensor is going to be replaced by an auxiliary field, right? So that's the decomposition. So basically, we have this problem on a lattice of the scattering of involving 4 sites, but you can think about e to the minus tau v, this 2-body thing, through the Hubbard-Stromic transformation, where you map it into this picture, my poor depiction of what we're doing with this lattice, which is we have a many-body propagator that has this form involving 4 sites. But you could write this, you could think of it as a 1-body propagator involving 2 sites, living in some background that are auxiliary fields that are external potential, right? So this is stuff we're familiar with, but it's important to reformulate this to tie into electronic structure. So we can always think about the many-body propagator as a linear combination of independent particle propagators in external fields. And the external fields are the purple random landscape that comes up. So I showed you how you deal with plane waves or Gaussians or one-year functions or really any basis you want, right? You could write it in this form, and you're going to get order m size of the basis auxiliary fields if you do this general thing. And that's a crucial. Until you do this, your cost will be too much to really do ab initio calculations. So going back to things you already learned, ground state projection method, right? We do this. We start from some arbitrary wave function. We project it with this. And then in general, when we write the projector method, we meet the same initial function, but you don't have to, right? Any trial wave function will do. So you can evaluate the energy anywhere. You can evaluate an observable somewhere in between, right? So that's the ground state formalism. Now, we wrote out the many-body Hamiltonian this way. So in this language, how do you think about a mean field calculation? Well, just like in the Hubbard model, you think about a mean field. The problem term is this red term, right? This blue term is easy. It's an independent particle calculation. So Hartree-Fock just means you take this 4C index and you bracket 2 of them. Bracket means expectation value. And then you have 2 left. So it becomes a 1-body operator. So that's Hartree-Fock. I mentioned density functional theory. One way to understand density functional theory is, for example, the local density approximation just takes this, it writes it in real space as a density operator, and then this thing is called an exchange correlation functional. It's a thing that's tabulated from calculation on the electron gas. So you tell me a density, I'm going to tell you what the effect of correlation is in a table. So once you do that, you've replaced H2, the red term, by a blue. So the whole thing turns blue. So basically, the philosophy of any independent electron calculation, a way to think about it is, and you'll see in a second why I'm sort of doing this convoluted introduction. The way to think about an independent electron calculation for a many-body problem is you change the Hamiltonian. You don't know how to deal with the many-body Hamiltonian, so you modify it. You modify it so that you can demand a single Slater determinant solution. Right? The solution to that problem will be a single determinant. How? So from an auxiliary field perspective, you can carry out now a mean field calculation. So you want to, as we said, for the ground state, you want to project this, right? I've just written the first order, the lowest order decomposition. Of course, you can symmetrize this to get a higher order product, but this is enough for us to understand the process. So I claim I could perform an LDA calculation using the auxiliary field framework. Okay, this is not how people typically do it, but it'll be important to understand what we do with the many-body context. So independent electron Hamiltonian, the LDA Hamiltonian we just said, is we change the two-body thing into a one-body term that's a functional of density, right? So then the LDA Hamiltonian depends on the current density. So you have to, the LDA has to be a self-consistent procedure. This is easy to do. We start from some random thing, random determinant. So we have this Hamiltonian. Now we can perform the LDA calculation. Start from anything that's a Slater determinant. Remember what a Slater determinant was, those orbitals and stuff. Write anything down. And this, I'm going to give it a superscript 0, denoting time stage 0. And then I'm going to construct this LDA Hamiltonian. It has this form. So H1, I already know. HXC, I look up the exchange correlation functional. I can compute the density because I have this wave function. So I compute a density. And then I put it into the Hamiltonian. Now I form the Hamiltonian. So I hit this Hamiltonian on the determinant. What does that mean? Well, we know from Thales' theorem that e to the tau, a one-body operator, hitting a Slater determinant would give back a Slater determinant. So this gives us a new Slater determinant. Later, I'll show you exactly the procedure, remind you the procedure. But this is one determinant. And in the language of AFQMC, what's happening is one path, right? You're tracing out one path. So this now has a new determinant. You repeat the same procedure. You take this determinant, compute a density, now I call N1, and then form the LDA Hamiltonian, hit it again, keep going. Eventually, this determinant won't change anymore. That's the ground state of the LDA solution. Right? You've done a power projection, you've performed the LDA. You could do Hartree-Fock the same way. This is not how typically you wrote your Hartree-Fock code. You did a self-consistency, but this is just as good. In fact, in some cases, better. I wrote a Hartree-Fock code to do the electron gas doing this, which is much better than the self-consistency because the size of the basis is huge. And this cost is one side basis, the other side number of particles. The number of particles is much smaller than the size of the basis. So you could do this. And as advertised, you end up with a single determinant solution, right? As you demanded. Now, building on this, how do we think about the many-body calculation? Remember, we already did the Hubbard-Stromowicz decomposition. We could write this as a sum. That's the tensor decomposition, sum of one body squared, right? Now, e to the minus tau h will look like h1, and then this is the Hubbard-Stromowicz transformation in general, Gaussian. So in parallel with this, we have one body, but with fields. So this we're going to use shorthand. E to the minus tau h is probability density function Gaussian in this case, but it could be a discrete binary distribution. And B, any B blue is like the B we were writing yesterday for finite temperature. It's an one-body operator that depends on the field, depends on the details of your Habermas knowledge. But nonetheless, it's a one-body operator. Fowler's theorem, we already said, one-body operator operating on a determinant. So phi means a determinant, gives another determinant. Okay? So then, based on this rule, you can carry out this propagation as a multi-determinant projection. Okay, so I'm going to repeat this procedure now for the actual many-body Hamiltonian. Okay, so as I said, the reason I'm going through this is to understand how you can formulate a many-body theory that builds directly on top of density functional theory. So back to this, again, we just want to carry out a procedure for projecting this in a many-body Hamiltonian. So one step of this is an iterative process. When you project it, current wave function, apply e to the minus tau h, next stage wave function. The wave function can be thought of as weighted sum of determinants. The determinants will be random, and we're going to call them random walkers. For now, the weights, think of them as one, right? So you're going to try to make them as uniform as possible when you sample something so that, all your samples contribute equally. So the weight has to do with, when we do metropolis, the acceptance rate. You want the acceptance rate to be as uniform as possible. So then you can realize this procedure, if you think about it, your current wave function is being represented by a linear combination of determinants. Then you can plug this in, you get the operator we want. So probability density times one-body operator integrated times this thing here is supposed to lead to a next stage, right? Okay, so there's a simple little algorithm that says how you perform this. You sample a signal. So for every walker that you currently have, just like in an LDA, make up something, initial wave function. For every determinant you have, you're supposed to propagate this by one step. You could do that by picking a Gaussian, a field from a Gaussian, then apply B to this determinant, which leads to a new determinant, and then update the weight. Okay, what do we mean by the weight? Well, the weight, according to this, there's no weight. If you could sample a Gaussian, you just multiply B to that, you get a new determinant. Where's the weight? Well, when you multiply a determinant, which is perfectly proper, by a B, eventually its normalization changes. This is the same step that you do in your normal calculation of when you do the modified Gram-Schmidt or you do the SVD to stabilize it, because you multiply a bunch of orbitals by some numbers, they're going to grow or shrink. You have to keep them orthogonal. So when you do that, there's a new normalization that comes out. So think about the phis as being proper determinants. Proper means each orbital is normalized. They're all orthogonal. So to keep that, a weight comes out. Right? Different determinants have different weights. So, okay, now we're going to perform this many-body thing, right? Remember these rules. We want to go one step from a determinant to a next determinant. A step is just a simple rotation, right? So this little orbital I wrote before, I'm just carrying two electrons just to show you. So one orbital looks like that, the other one looks like that. They're just written in terms of the basis. What do we mean by operating B on this determinant? Well, B has this form, e to the field times a one-body operator. And the auxiliary field variables are here. So this whole thing is a, sorry, we already said this. N is the size of the basis, and the number of columns is the number of particles. So the one-body operator is an n by n matrix, just like we talked about in finite temperature. So the n by n matrix multiplied to the n by 2 matrix gives you a new n by 2 matrix. And you can orthonormalize them. So that's a new determinant. Okay, so now you can think about a many-body calculation in terms of what we've talked about so far as just recovering many-body effects as fluctuations around, I used LDA, but really any mean field, right? So the many-body Hamiltonian is LDA, any mean field Hamiltonian, plus a two-body term. That's a correction. You can use the actual Coulomb minus whatever mean field estimate you want, and that's delta V. So we already talked about how the LDA can be formulated as an iterative process. Right? So in other words, if you measure the overlap of your random determinant with some target, and think about this as the exact many-body wave function if you want, then you start somewhere and you're going to project this iterative procedure we demonstrated. You're going to converge. Eventually, it doesn't change anymore. That's the LDA solution. So the many-body calculation, we wrote down before. We need the LDA, and then we need this correction. This correction is done through the Hubbard-Stratanovich, and you have the sampling. You have the integral over fields. So when you do the procedure I said before, you pick Gaussian fields, you multiply them. You can think about this as just creating all kinds of different random walk paths around the LDA. And so that looks like this. In Fock space, the LDA, you can start from anywhere, you converge it to a local minimum. So you can start from these different trajectories, you converge to this local minimum. And then you can start from here, all kinds of solutions, and then this random walk for the many-body thing will start out going different directions. And these determinants as a whole represent a many-body solution, right? Linear stochastic representation of a many-body solution. Okay, so that's basically an algorithm that you can carry out for any many-body Hamiltonian, one and two-body terms, any electronic many-body Hamiltonian. So we already talked about the sign problem. In this context, how does the sign problem arise? So that's the mean field, and this is fluctuation. I've drawn you a very friendly case where the fluctuation is not very big.
Very nice. Is there an issue of double counting or things like when you do double? I mean, when people do LDA first and after they do correlations, there's always this issue of double counting, et cetera.
Yeah.
What is included in the LDA?
Yeah.
And then you put in your V back in, so you somehow double counted the electronic correlations. Would that because
this does not.
Because
this
your
is
LDA
rigorous because
your LDA is somehow does include some type of interactions, right?
Yes.
And so your V, what is your delta V is
So the LDA, so this is this process is rigorous in that we're just writing many-body, the actual many-body, which has the form of K plus V. This is an interaction. I can always write this as K plus V
so you have the LDA minus
little v LDA.
and then you take the V minus V LDA. Okay. Okay, good. So that's your delta V.
This is a one body. I'm always allowed to do this on the Hubbard-Stratanovich. Yeah, yeah. So the whole thing, theoretically, you didn't have to, you could just do the bare thing. But in practice, if you do this, it helps you. Yeah, exactly.
So if I understand correctly, the red curve basically is the path of each walker, and then effectively you average over and you should get the same curve as the mean field. But so why? So then it's just, I mean, we already have the mean field result, or is it just as a benchmark?
There's a crucial, so this is the mean field. The red curve is equivalent to one path in how we do the projector Monte Carlo. The sum of these is not the mean field, but rather the many-body answer. The sum of the red curve is the many-body answer. It's just like how when we do projector Monte Carlo in ALF, right? We sample each path, and then we do a computation in the middle to compute expectation value. It's because we're summing over many paths.
Yeah, okay. Yeah, thanks.
So how does the sign problem happen in this language? Well, I've drawn you again this overlap, projected overlap with an exact wave function. And of course, I don't know the exact wave function that's depicted in green, but really for this test, you could use any wave function you want. It's a random walk. If you monitor its overlap, it could become zero, just like that picture in finite temperature that we drew last time, right? So as I start from here, I could set up an initial mean field solution that has a positive overlap with my target many-body wave function. If it's negative, flip the whole sign, right, to begin with. So they're all positive, but after a while, the random walk will hit a 0. Once this starts, it's the same picture that we talked about before in finite temperature. A path that continues from here can be both positive and negative. This is because the many-body wave function, right? You have a linear solution to a Schrodinger equation. So if psi, the overall wave function is psi, you could stick a minus sign in front of it. It's still a solution. So there's a degeneracy between this family of paths. And if you take this whole thing, imagine this is water, you have an image under, that whole family is also a good solution. Right? So once you hit this 0, you cannot tell whether you belong to the upper family or the lower family. They're the same. So you're going to start picking up random noise. So eventually, the ground state means you go on forever to the right, and you just have a mirror image of the two mixed together, and that's the sign problem. You have no signal at all, right? The final answer will be complete noise. So that's the sign problem in a ground state picture.
Okay. Generates a phase, not only a sign.
Exactly, it's coming up. So I'm going to dwell on the sign for a couple pages just to remind us, reinforce the intuition from yesterday about the sign. Okay, so this is why if you were doing a ground state projection, long enough projection, right? You sample all the paths. Basically, you're sampling random path. They have nothing to do with the ground state, right? Eventually, they're just all random half path. So plus and minus, there's a symmetry between them. That's what I'm saying. So the recipe, of course, we talked about yesterday is we constrain the random walk, right? We stop them when they hit this projected 0. And we talked about how in finite temperature we could realize that. So why is it you might argue in a finite temperature context, well, you need to map out exactly as you trace in history how this is going to be a 0. That seems very hard. So in this picture, maybe a little more intuition about why this is a good approximation. So what happens when you become 0, when you exchange a sign, or the upper and the lower plane? How do you distinguish them? Well, you go from a positive to negative, you have a determinant like this, right? One orbital like this, the next orbital like this. I'm just still using a 2-electron example. So how does the sign problem happen? Because your determinant swapped sign, right? Your determinant picked up an overall sign. This is plus, and you could pick up a minus. How do you pick up a minus? Well, you have to exchange the two orbitals, swap the two orbitals. So stochastically, you have one orbital on the left first, and second, you random walk. As you randomly walk, you tweak it's like spaghetti. You're turning around these orbitals by rotations and stuff. Eventually, you have to swap the two to get to the negative region. That's a big change, right? So what I'm asking you is, can you tell me, classify them? Is it positive or negative? Is the red orbital at number 1 or at number 2? You can imagine that classification does not require a huge accuracy in your test function, right? You have a determinant, you should be able to compute an overlap and roughly catalog is it positive or negative. In other words, the super exchange requires typically energy barriers to happen, right? You're swapping energy levels that are not the same. So this test is to determine if a super exchange happened is typically a very accurate test. And that's why the approximation is good. So as Johannes was pointing out, well, so far it's not just this super exchange, there's a phase. So how does the phase happen? Well, the Coulomb interaction, when I showed you the plane wave, you see that we had a rho q and then I rho minus q or something. There's a phase, there's a complex set of fields. So what's happening instead of the picture I showed you before is actually this. Now I'm depicting a complex plane of the overlaps, real axis, imaginary axis. You start on the real axis, before you just stay on the real and you hit a 0. But in reality, you're actually doing a full-blown three-dimensional walk like this. Right? You're going anywhere, you're developing a phase. So how do you control this? Well, the same argument that if you have a wave function, that's a solution. Then e to the I theta is also a solution for any e to the I theta. So there's a total degeneracy of the gauge. So you need to constrain your projection to one overall phase, right? You pick one phase and you stay with it. But how do you pick one phase? Because in between, when you apply the Coulomb interaction, it's turning the orbitals around. Some of that phase is legitimate because it's trying to pick up the interactions. So you need to distinguish what is a legitimate evolution of the orbitals with phase, what is a global phase. And that's a gauge choice. So, so it turns out this gauge choice, it's crucial to apply an imaginary dynamic shift of what we call force bias before you constrain the phase. And I'll show you next page what it means. But after you do this, this is for silicon calculation. If you don't do anything, of course, you project for a short time and then it goes crazy, right? The sign problem goes in. After you do this, the green curve is what happens. Of course, you have a normal calculation, you have a polynomial calculation. How do I know this is very good? Well, this is actual material. When we first try to do this, we try to compare, go to infinite size, compare with experimental measurements of the bulk modulus and the cohesive energy and so on. Later development, we could do, for this system, we could do constrained calculation and then release. And it turns out this is basically exact. But for now, let's worry about the algorithm first. So here's a little too much math, but I want to make a connection with the Timble. So this is how we do the after the Hubbard-Stronach. We have a Gaussian, and then we have one-body operators. And we were doing iterative projections like this, right? Phi, we apply this operator, we go to a new phi. This is one step of the random walk. So instead now we're going to introduce importance sampling. We're going to shift the contour. So this is as good a representation as that. In other words, I could introduce an arbitrary shift. If you complete the square, you see that it's x minus x bar squared and then b x minus x bar. So I've just made my variable, Gaussian variable x here, x minus x bar. So the operation I did on the top line is x goes to x minus x bar, sorry. But I'm going to allow x bar to be complex. Okay, so that's a contour shift. Because I'm supposed to do this integral, I can shift the contour. So, and below we'll see where we want to shift it. So basically this iterative projection, now I'm going to introduce importance sampling. I'm going to think of the projection as that. This looks kind of messy, but if you look at it, you see two things. You see, one, I've divided, before I hit the phi, I've divided by its overlap with some trial wave function, and then I multiply it back by the trial wave function with the new one. So this is the future. So in other words, I want to know if I'm going from phi to phi prime, I want to know the projection of phi with some trial wave function, my best guess now. I want to know the projection of a future position I'm proposing, and I want to know how they compare, right? So this is the usual trick of importance sampling, right? And when you're going from A to B, you have some idea of what you're trying to sample, then you want to do a similarity transformation to change your kernel, how you propose things, so that you bias it toward the position you want to be. Now, notice that when you iterate, this will cancel, right? Because the next step, you're going to divide by the current position, which will be phi prime now. You're going to divide by that, so it cancels this multiply, and it just iterates, right? So you're doing the same iterative equation, but with modified kernels, similarity transformations. Okay, so once I do this, I can minimize the phase. So when I do this from here to here, I develop a phase when I allow this shift. When I apply the original thing, I'm going to go from here to here. I'm going to develop a new phase. But given my best estimate of the phase, I'm going to make this whole process stationary, okay, to leading order. In other words, based on a trial wave function, I can estimate when I go from one position to a next, what part of the phase is an internal structure due to the interaction, what part is a global change. And then I'm going to take out the global change. So I minimize the phase in here. And this little diagram says that in this complex plane, I'm currently here. I can always assume I'm currently real. There's and I propose to go to a new position here. And I can project, okay, when I go to the new position, my phase difference is this ratio. Right? So in other words, I'm trying to develop a phase, overall phase in front of me. And I can then shift my contour dynamically depending on where I am now, so that the extra shift does a phase that cancels it. So based on this, so by minimizing this phase change, I can obtain, you work through the math, the correct phase shift is this, which is complex, because V is complex. The operator V after you do the Hubbard's triangle is complex. So this is basically, in my view, a local Timbal, right? Anywhere I'm going in time, rather than trying to find the Timbal for the entire path, I'm trying to go from one side to the other. Locally, I find the optimal phase. And of course, I don't have the problem of trying to search, trying to prolong the time, the scaling problem. I can compute this very cheaply, just like in heat bath, right? If you apply this to the Hubbard model, all this is when you sample the up or down icing field, you compare the two, right? And you decide the phase. So this computation is a local computation of the one-body operator. And yeah, so I've not been successful. Some years ago at the INT, I sort of, well, less explicitly, but I suggested when people were starting from nuclear physics to consider Timbal, I suggested that we had already sort of had this idea, but that obviously didn't stick. But now I'll make this claim again, that basically this is the basic idea of Timbal, but it's a realizable, approximate way to realize. Okay.
So it's not just an optimal contour deformation more than a thimble. I mean, a thimble. Microphone. Very good. Is it not just an optimal? It's just an optimal contour deformation. The thimble, basically, if I understand well from your talk, is really you have a fixed point and there's a thimble attached to a fixed point. You don't have that, right?
So it's a dynamic.
It's a dynamic. So you're just somehow deforming the contour.
Yeah.
But thimbles are not just deforming contours, right? The thimble is more finding the saddle points and attaching a thimble to a saddle point or to a critical point, etc.
Yeah.
So this is much more that it's between the two, right?
So
I mean, I know. So help me. There's many thimble specialists here.
if you are going in the spada, you have a path, and you're trying to, with the thimble, my understanding is you're trying to find the optimal sort of entire thing to deform your contour so that you minimize the action, right? So what I'm doing is I'm just going from one side to the other. Every step, I find a different contour integration, a shift, a different shift, a small shift, and I map this out. So every step of this is approximate in that I involve a guess, right? So I don't try to evaluate this whole thing to get the thimble, but every step I minimize the phase. So the philosophy obviously is different. I'm not saying they're the same thing, but I am saying I think there's a fundamental connection in the idea of trying to use the contour shift to minimize the phase evolution, right? And what you minimize is different because I've taken the conservative approach of saying, I don't know how to minimize the whole thing because that kind of, to me, involves solving the problem. But I have good guesses. I have reasonable guesses, well, assuming I do. If I don't, the approximation is off, is,
Each walker has his own thimble.
yes.
So there's a walker dependent thimble, which is.
Walker and position, walker and time. So this is one walker,
It's not a property of a path integral, it's a property of a walker, right?
yes.
But, okay.
It's the same thing, right? It's a, so this is one walker. So by the time the walker, so in a normal calculation, if we carry the whole path, we predict a beta. By the time the walker completes, it's a whole path, right? So I'm just saying, I want to construct this path rather than having the whole path and do metropolis. I want to construct it as a branching random walk. So this goes, of course, this this walker somewhere can branch into two pieces, but then you would just view that as two paths, right?
It's a shift, but it depends on every.
Well, maybe you could try to get the, sorry.
It's probably something like imagine we would have local updates in usual finite temperature auxiliary field, and then after each update we would try to shift also locally fields in complex plane and try to optimize phase at this current update. Something like this, I think.
So like that, but I would reverse the order. I update according to the shift. So I don't already go there and then discover I have a problem, but rather my sampling knows, right? So the sampling is built into this.
You do
because
this
the shift
estimation
is-
before, basically.
Yes.
Before doing
And
that,
then you
right?
do the sampling. It's absolutely crucial. If you do the sampling first and then do this correction, it's just a weight that's going to multiply.
The key is that your sampling is sequential.
Maybe.
Yes.
That's it.
So
Yes.
you can't do that in the
Yes.
kitchen. Yeah.
Yeah.
Yes.
You cannot, all these things cannot, it's very, all these things are very hard to go back into the BSS algorithm. Because you lose you somehow, you
The-
lose the notion of the past and the future.
Yeah, as I
Uh-huh.
said yesterday, it's to sort of, it's with great reluctance, we make this branching random walk, right? Because the BSS, the Metropolis has a lot of advantages. You could compute things in the middle. We had to do this because of ergodicity, right? Because if we try to carry the whole path in even the constrained path situation, we're guaranteed to be stuck somewhere, right? We have an infinite ergodicity problem to impose the constraint. Like I said yesterday, the probability that you find this path is 0, right? If we try to carry the whole path. That's why we broke it, right? So, but once you break it, it's a local step-by-step procedure. And it's compensated by branching, right? The reason that you don't have to run out of path is because the ones that don't hit the node will grow, right? Normalization. So it's like you already, rather than trying to, think about a particle in a box, right? Rather than trying to deal with a ground state that's all symmetric simulation, you deal with an excited state, but you constrain it, right? So you can always filter out the excited state.
Can I ask a question?
Yeah.
So maybe now the picture has changed, but previously when you had the picture of the walkers and in the case of the real sign is just real. So there kind of you kill them when they hit 0.
Yeah.
So now it's a phase, and it's not clear how often in that same picture. It's not clear how often it will actually hit 0.
So it doesn't. So 0 is now not your main issue anymore. So rather, so in this case, very good question. Think about. So in this case, this random walk, if you depict it in a complex plane of overlaps, right? So imaginary. And what I mean is it's one walker, you follow its history. So maybe we should, right? So it's as a function of n, right? You follow its history, you can start here and you're going to move around. And in general, the moving around is justified. If you don't do anything, it's just going to move around because of the Coulomb repulsion. But now with this contour shift, what's happening is it'll still move around. But by your approximation, you now argue that the moving around, the development of the path, this picture here, is fake because it's been canceled by the weight to leading order. So basically, the extra phase that it develops is a fake phase, so you can project it back. So it would walk, and then we would do this cosine delta theta. This is delta theta. We project this back. So we decrease the weight if it picks a phase. We decrease the weight by cosine delta theta. And then as an effect, it stays on this axis. So this zero is zero measure, but it won't cross anymore because if it flips 90 degrees, it'll be
So
projected
in the
to-
limit of zero step size, again, I guess your shifts would be exact. They would exactly,
It would be, no,
they would exactly
it's
remove.
exact with your trial thing. You don't know the, right. It's exact with this. If you put inside zero, I would be exact, right? I would know exactly how to cancel the phase. But now I'm approximately canceling the phase.
But are you approximately canceling, would that, but as you have smaller step size, you cancel it better and better. Is that true?
No,
No.
I cancel it, again, subject to a Trotter error, which is very, very small. I cancel it precisely by this, by psi t. But again, not by psi zero. I don't know how to, I don't have the ground state. I don't know how to cancel it by psi zero, right? That would be the exact version of this. That's the theory, right? So it's the same as talking about the finite temperature, assuming you know all the BTs exactly. This is the theory, again, the foundational theory of this whole thing is that if you assume that you know this, you have an algorithm that recovers the exact answer. And that's the limiting case, and you work toward that.
So you always measure the phase with respect to a reference state. In an ideal world, the reference state would be the ground state, and then we get the exact answer.
Yes.
But since we don't know the ground state,
Yes,
we can't measure the phase, so we come up with an approximation of
Yes.
the ground state.
yes. But recall the argument before about, so first of all, the ground state, the overall phase doesn't matter, right? You could pick any phase you want. So that's not its issue, but it's its content when it evaluates this that makes an error.
Yeah.
But the error, recall the argument of swapping two orbitals. By the same token, evolving an overall phase is not trivial, right? It's not as difficult to predict with a file wave function as the actual content of the orbital. You're just saying, hey, you've hopped a different phase, different gauge, and I want to put you back.
So if you have a better trial wave function or a worse trial wave
Yeah.
function, in the sense that the overlap with the true ground state is large or
Yeah.
small, will you mechanically see the difference as your algorithm is running, or will you only see the difference at the end when you look at some consistency checks with observables or something like that?
So it's a iffy answer in between, right? Because as you need to accumulate enough statistics to detect the difference between two. And the statistics would be that the noise would be smaller if you have a better one, because it's rebelling less, right?
Okay.
And of course, your final answer, you could
So
see
if
the error
your
bars
if your
also.
precision is better, then it's more likely that your accuracy is better.
Yes, the precision is tied. So when you put the final algorithm together, there's basically a fluctuation of the local energy as you project with the Hamiltonian, how much it's pushing back against this. So in a perfect case, it would just be steady. There's no noise anymore. So you the variance tells you something, but typically the variance is hard to gauge, right?
Yeah.
The kind of typical classes of wave
Are
functions.
there pathological examples where it's not the case, where you
Yeah, it could be if you picked an excited
in-
state,
in-
for
in
example.
whatever you try? Huh?
If you picked an excited state, it could be happy. It's trying to project to an excited state,
Ah,
right?
I see.
Because that's also an eigenstate. So if you project your excited state is orthogonal to your ground state, and somehow your Hubbard-Stronach transformation does not tunnel between the two, right? If it tunnels, it's going to try to collapse. So that's a case where you're going to see spikes. But if it's a safe calculation, like different symmetry sector, it would happily do that. Just like really any projection algorithm, we could target an excited state if it's symmetry protected.
So this is the idea if you have, say, an SU2 symmetry that you preserve for every Hubbard-Satonovich, you know the ground state is a singlet,
Yeah.
but you start with the triplet state.
You'd be happy.
Find the ground state of the
Yeah.
triplet sector, but
Yeah.
you don't find the singlet. I see.
Good. Any other questions?
Is it means that if in this case, if we choose the I mean, shift the false bias is close to the correct one, then, I mean, the weight in this plot means that the weight of the complex file is close to the real axis.
Yes.
So you can.
Yeah, it basically, the random walk doesn't try to leave the real axis anymore.
So you can just use a simple projection to return to the real sine curve.
Right, right. So that, again, it's absolutely crucial. You need a dynamic shift, right? Where you are, it matters how much shift you need, how much of a contour deformation you need. How much time do I have, by the way?
35 minutes.
Okay, lots of time. So any other questions on this?
I also have a small question is, this important sampling, I remember is that we first do the Gaussian sampling from the field.
Yeah.
And then we act in this, but is it the important sample is just reflect from the weight?
Okay.
Yeah, because.
So I don't know how many people are familiar with sort of important sampling and how I'm referring to it. I know that there's confusion in that sometimes metropolis sampling is referred to as important sampling. That's not what I mean. Are people familiar with sort of this type of similarity transformations? Why that's an importance sampling?
It might be worth repeating your idea.
Okay, so I'm going to give you a little example to illustrate this. Where do we have an eraser? Okay, a little example, maybe it'll help you see this part better. Consider this integral equation. I don't remember the. I think this is maybe there's a half, I don't remember. You could check this quickly. This is an integral equation. Psi, eventually there's a solution. So psi y e to the minus y squared, this kernel, and equals that. So this is of the form right? The integral equation that has a solution. You can think about this as a random walk because you can just use this sample and y1, y2, yn samples that represent the probability distribution that's psi y. We're assuming that it's positive. Well, this is a weight. So in other words, for each sample, y1, you can evaluate w1, and you could say the weight is that much. Okay, and then this is a Gaussian. So for the position y1, you pick a new x, you go to an x. So that gives you a new representation, x1, x2, xn prime. The number doesn't have to be the same as this because there's a weight. If some walker's weight is too big, you might want to split it up into two and so on. So this is basically a branching random walk. Okay, you can realize, in other words, the punchline out of this messy thing I wrote is integral equation can be solved, simulated by a branching random walk, where branching random walk. Okay. So it turns out the solution to this problem is psi of x is equal to e to the minus half x squared. Okay. So I could do an importance sampling transformation. I could write this as psi of x how do we call this? Maybe f of x is an important function. F of x e to the minus half x minus y squared, e to the minus y squared, and then f of y, psi of y dy. This is sorry, missed two things. Thank you. W of y, and then f of y. Okay, now I could call this my new psi tilde. It's still an integral equation that has a solution. Okay, but now if you suppose you cheated, well, actually you could try. So take f of x to be, e to the minus a half lambda x squared or something, right? And then you can do this transformation together with the y. It turns out this whole thing would be e to the minus x minus y minus plus a half y or something squared. This whole thing. If you took for lambda equals 1. In other words, when you do perfect importance sampling, you cheated, right? The answer is e to the minus 1/2 x squared. If you put that in here, this whole thing, the new kernel, okay, x, y, tilde is just equal to that. It tells you, okay, so give me a y, shift the position of y by a half, and then sample a new Gaussian, and everybody is weight 1. Everybody's perfectly executing the random walk. There's no branching anymore. The whole thing converges. Okay, so if you make a lambda that goes away from 1, it'll be a little worse, but you're going to see the fluctuation of w. The transformation will be this times a w tilde. W will fluctuate a little more. Your original w fluctuated a lot more. So this is the idea of importance sampling, is that if you built in some knowledge about the thing you're targeting, your fluctuation, the random walk, will behave better. Okay, so this is what I meant by a transformation. An importance sampling transformation, and branching, the idea of branching random walk. So in this context, it's exactly the same thing. You have these determinants and they're branching, but if you predict where they're going in their phase and you take that out, there's less to sample. Okay, so I forgot, there's a second reason why we took this detour, but questions on why, how this relates to it. I forgot why we wanted to explain random walks. That's purpose number 1, and number 2, we wanted to show importance sampling, and I think we did both. But there's a third reason why this was triggered, which I forgot.
Yeah, I just asking where about the importance sampling. I think I don't get the third point, I think.
Okay, so that's the reason, and you can see this is doing that, right? You divide out this importance function, you multiply it back, but remember, when you divide it, you're dividing your current position, the importance function. When you multiply it back, I wrote it inside the integral. It doesn't matter, right? The integral is with respect to y, so this goes outside. But this knows about the new position that you're going, which is fx. And that biases the whole thing, right? You divide your current position, you multiply by the future position so that you push it that way. That's the idea of importance sampling.
In the phaseless approximation, I'm trying to understand what's the similarity and difference between phaseless and constraint, the original constraint path.
Yeah.
In the constraint path, you basically kill walkers when they cross the zeros.
Yes.
In the phaseless, you never kill a walker.
Yeah.
Right. So let's assume, okay, that's correct. So there's no, it's just different. There's no
You
There's no
slowly
going
kill
from,
them.
sorry?
You slowly kill them because the constraint path, it's a plus or minus
Right, right,
binary
exactly. Boom.
situation. So
yeah.
here you're killing them by this projection.
Well, you're not killing them. You keep them in your.
Yeah.
The only way to
But
only
you
kill
project
the
them
walker
by
is by the
cosine of
population
delta
control.
theta.
Sorry.
So
Yeah.
you project the weight by cosine delta theta.
Right.
So
You will
you gradually
decrease the weight, and then you will kill them
As a
in the
function of-
population control.
Right,
Right.
right, right.
But in the constraint path, you really kill them, not only by the population. Well,
It's also by the population.
it's also, of
if
course,
you
also
want.
yeah,
Right, but it's a binary choice.
binary choice.
Now, the reason I was trying to sort of struggling to distinguish the two or striving to distinguish the two is this. If you normally, well, at least how I approached it, thinking about constraint path and then trying to generalize this, was to think about, okay, well, in the case of constraint path, I have plus or minus. Here I have a phase. So I should constrain the random walk to half the plane. That's the most straightforward generalization of this, is that you let this go until the real part is negative. So it turns out that's wrong. And the reason you get bad answers. And the reason that's wrong is what we've been laboring, which is that there's a part of the phase evolution that's genuine. It's trying to get the electrons to stay apart to reflect the Coulomb interaction. So if you just do this and then push it back, you're kidding that. So without this this phase, this force bias thing to offset the phase, to make the phase balanced and zero, if you kill them, you're kidding off the Coulomb interaction. So once you do this phase projection, you could execute the constraint path. You could say, so I did this cosine. You could also just let the walk wander half the plane and then stop it. It'll also be, we cannot distinguish the answer. They're basically the same. So the crucial thing is for the random walk, to separate the two, a part where this phase is developing is random, right? It's not an actual internal structure of the determinant that developed due to the Coulomb interaction. So that part is turning and you cannot stop it. If you stop it, you make an error. But once you do this, it's balancing, it's oscillating around this axis. The choice we went most commonly is this cosine projection to put it strictly on the real axis. But as I say, you could also just let it wander and kill it off at the real part becoming negative. Same answer. But if you had killed it before you do this contour shift, this Timble thing that we're referring to, right? This complex shift, then it would be incorrect. Okay, so that's a subtlety that took us multiple years to figure out. Other questions?
So if I have a model, right, and I can formulate it in a complex way and I can formulate it in a real way. So then what would you do? Would you prefer doing it complex and use the phaseless, or
We prefer to do it in a real thing.
but that means preferring, that means there will be a difference, right? There'll be, if I take the same trial wave function to guide it, I will have a difference if I do the
In the
phaseless.
Hubbard model, it looks like there's a difference, right?
And the
in the
real
charge
way-
decomposition with this phaseless is not as good as the
Right,
constraint
okay,
path.
okay.
Okay, so just a couple examples. This is a recent thing by my student, Siyuan. So this is like trying to optimize silicon, the structure. So imagine you put a bunch of silicon atoms together and you mix them up in some random way. So this looks like that. Some cut through the supercell looks like that. So the final structure of silicon looks like this. So you put the atoms in there, in this structure, and then you start this simulation so this is not one simulation, right? What I've told you is one Hamiltonian. One Hamiltonian means the atomic positions are fixed. This is now doing molecular dynamics or doing optimization, connecting. So I have the atomic positions. I can ask, given these atomic positions under Born-Oppenheimer approximation, what is the force on each atom? And then I'm going to move the force, move the atom so that I want to find the optimal structure in silicon. Pretending that we don't know silicon existed, we put a bunch of silicon atoms together. We ask, what is the final structure, equilibrium structure, right? So this is beyond, so DFT also just does one structure, but the Carl-Parnello version of molecular dynamics DFT does this. So this is the equivalent now, replacing the DFT part of Carl-Parnello molecular dynamics with QMC. So we start from this structure. We optimize the positions of the atoms according to the many-body calculation of the electronic structure, the ground state wave function, and the forces on each atom. So it goes through stages, goes from A to B is here. This is after some steps. It looks like that. And then C looks like this, slightly off. And then D, this is a measure of the slope distance against experimental structure. And the horizontal axis shows the energy of the structure. So you can see the energy is coming down as you optimize, but as you get closer, it's sort of moving around. The energy is hard to distinguish, but eventually it gets down to the right structure. Right? So this is a recent development where we can compute forces, and that in electronic structure has been a big problem. So this is now not just forces. This thing, the atoms stay in a fixed volume supercell. And this one, the volume, the cell shape is being distorted as well. So we compute the tensor for this. So this is aluminum nitride and put in a cell. And we started with this structure on the left, which is wrong. And what's being monitored here are a few things. This is the lattice constant in one direction. And this is like a C over A ratio. So C, it looks like this. So lattice A, and then C, this direction. C over A ratio can be modified. And that's the second panel. And the third panel is the angle between A and B, this two bound. The angle also changes. And you start from this position, which, for the three quantities are here. And then you do the simulation. Eventually, the ones that are correct stays correct. The ones that are wrong gets corrected. And the little bars are the final result with error bars. And the dashed lines are experimental measurements. And so you can now ab initio predict a structure. So this is the geometry and structure optimization in solids. Of course, again, this involves many, many, many of these calculations. For each Hamiltonian, you need to compute the Hamiltonian parameter. You need to compute the ground state to get the force. And then you optimize this with classical molecular dynamics. Okay, so a little bit of transition metal chemistry. This is from last year, a cover paper in Journal of Chemical Physics. So it talks about transition metal molecules. So this little cartoon basically depicts, so it summarizes an effort. This is in collaboration with the Columbia group of Reichman and Frisner, two chemists. So this cartoon kind of depicts what we did here. So we start from a bunch of transition metal atoms. We compute the energy that it takes to exit one electron from the atom. It's called the ionization potential. In solids, it's a little, it's a gap, right? Atom, and then we do the molecule. We compute that and also dissociation energy, what it takes to break the molecule. And then it becomes more complicated. There's a transition metal and a bunch of organic atoms around it. And then it becomes more, it's a pancake with a transition metal, and then this, okay? We keep going. And the horizontal axis shows the error. And these are benchmark set. Each has 20, 30, 40 molecules or something. And this is the computed answer minus the experimental measurement as a benchmark. And the blue line is supposed to depict chemical accuracy. In other words, if you reach that accuracy, you can predict reactions. And that's the goal in chemistry, is you need to get into chemical accuracy. And the current methods are density functional theory, and this is all over the place, different places. There's no chemical accuracy for transition metals. Now, for organics, it does quite well. And I'll mention the current gold standard in chemistry that does very well. But with this method that I've been telling you about, we've been able to so by last year, this paper, we're here, and it's systematically within chemical accuracy. So This is a little bit earlier. This is simpler, just dimer, realistic. This is a large collaboration, Simon's collaboration on a many electron problem. And we did this for just transition metal molecules. This is simpler. And basically, it's simple enough that you could perform highly accurate calculations. And what this is showing is the error in taking the molecule apart, the energy. A bunch of different methods that got benchmarked, a lot of LDA and different many-body methods. So the calculation with AFQMC is here, and you can see that the two ionization potential and dissociation energy, and this little vertical shaded line is the chemical accuracy. So it's systematically over these 20, not 20, I don't remember how many, maybe 10 molecules, that's the error. And there are some that are doing better, but if you look at them, they're all exponential scaling methods, right? So those are the benchmark methods. So except for this one, couple cluster, which is the gold standard in chemistry, and that has an n to the 7 scaling versus QMC, which is n to the 20, n to the 3rd. And here, couple cluster does comparable or better, but you're going to see, because these are simple molecules, on the next page, I'll show you more complicated. This is one of the examples shown in that cover page story with these dimers. So this summarizes, this is done by James Shi, who now has his own independent group at Rice. The bond dissociation energy of 44 3D transition metal diatomics. And we benchmarked 10 different DFT functionals, and then these couple cluster, which is, as I say, the current gold standard in chemistry. And you can see, so the absolute mean absolute error is on the left, and you need to target a couple, this is kcal per mole, something like this to be chemically accurate. And this is not quite there. And this is, the right is this red bar that shows the maximum error, and the maximum error needs to be within a few too, right? Because otherwise you have outliers you don't know about. So AFQMC falls into this comfortably, systematically reaches chemical accuracy, and here you can see the gold standard actually does not get there for transition metals. Now, we were more proud that when we did this, we actually cheated. The whole set has, I don't know, 40, what did I say, 44. This tabulation is with 42. We left out 2 that we didn't agree with. But we questioned those 2 experimental answers because they were outside our error bar by quite a bit. And since the publication of this paper, those experiments have been redone, and they agree now with theory. So how much time? How are we doing?
15 minutes.
Okay. So I'll briefly mention just a recent thing, trying to release the constraint. So technically, so basically the idea is really simple. You've done these constraint simulations at some point, and then you've gotten to a really good ground state, but you're biased. So can you now lift the constraint and run for a little bit longer and see what happens, right? So the idea is really simple. Technically, it turns out to be challenging because you've done these important samplings. Now, once you release it, you have to undo, otherwise an important sampling will keep your force bias the way it is and pushing according to what it thinks. So you need to undo. When you undo the important sampling, the places that are really off, right, according to the wave function, you shouldn't be there, but you really want to go, those will blow up, right? So there's a technical challenge. So what we've done is this idea of interfacing the branching random walk with the metropolis sampling to do this, and it turns out to be pretty effective. So the idea is this. So you're running now from right to left, you're running the normal constraint calculation, and you don't, so the idea is you start releasing here. This is imaginary time. But you don't stop there, you keep going for a while, because when we do in AFQMC, when we do a measurement, what we do is what's called back propagation. We go for a while, and then we come back. So now we just do this calculation, we pretend we're going to do a back propagation. We map out a path. And this path, then we stop, And then we take this part of the path with this part frozen, and we start doing our usual metropolis sampling on it. It turns out you can work out the math that this gives you essentially the ability, without undoing the important sampling, to interface the random walk that came, and the rest of the piece is a metropolis sampling. Then you can start computing things here. So this, now the released answer will be better than where we stopped with the AFQMC. So this is a particularly hard case, and it's trying to illustrate. So it's iron oxide transition metal thing. So you make a 6 millihartry answer error when you stop AFQMC. This is with a simple trial wave function, just to illustrate the point. And you can start releasing, and you see that eventually it converges. So this is the VASP. Some of you might know VASP is a huge ab initio package. The VASP group has implemented these methods, but not the metropolis release part. They try to do this on a set of molecules and compare. This is their first implementation. They pointed out that, so the dashed lines indicate error bars, error with respect to, I forgot what exact answer or something. For small molecules, these are. And these are also not transition metals. So they're relatively simple. But they demanded, with this trial wave function, they used just a single Hartree-Fock, single determinant. And this is the answer. The orange line is their answer. And we repeated some of these calculations. Yes, with a single determinant, you can see there's quite a few outliers that fall outside. By the way, the gold standard in chemistry is here, is this light blue. Also, some will fall out. And that's these blue things. And then we, for each of the blue, of course, we could do these for the ones that are already inside. Nothing will happen, right? But for each of the blue ones, we do this release, and it all falls. It all goes into chemical accuracy fairly comfortably. Okay, so I think I've mentioned the work I mentioned. I've mentioned the names explicitly, but this is sort of the more extended group and collaborators. At least let me flash this picture and thank them. So to summarize, I think QMC can tackle a much larger range of problems in quantum science. And I think, you know, the future is bright. We've seen this in the various talks. We should continue to seek impactful sign problem-free models and formulations and push the method, as you know, shown throughout the workshop and most recently by Peter. Even when it's not sign problem-free, approximations rooted in fundamental theory of what is an exact understanding will allow some of the most accurate computations possible. And that's sort of one main thing I wanted to introduce to you. And in particular, the method I've been talking about with constraint path or with phaseless, I alluded to at the beginning, decided to depart from models, but progress in understanding the Hubbard model physics. It's emerging as a general reference method in quantum chemistry. I think now with transition metals, it has supplanted what's known as the gold standard. It's a versatile framework for correlated materials, multi-band simulations, or larger scale with embedding, and so on. Many possibilities that can be explored. I think the one thing that you are all here, you believe in, but I think it's important to still point out is the maturity of softwares in our field, like ALF, right? Will really usher, I think, the community into a new era where we could do this. We could do a much larger range of problems. I want to sort of a little advertising to think of Flatiron for your future interactions and collaborations. It's in New York. It's a very active place. We have many, many visitors, not just computation. We're a computational center, but theorists, experimentalists. So you should think about coming to visit. And we have yearly postdoctoral fellowship openings, pre-doctoral PhD students who can spend time there. We also have a permanent staff opening we have multiple, but one in particular in QMC for softwares at CCQ. And so stay tuned for those opportunities as well. Thank you very much.
So question session?
Okay.
Can I quickly, I just wanted to ask if you could show again the paper where you had the silicon disassembled.
Yeah.
Let's put it that way. I just want to note the paper again because I find it really interesting.
This?
Yeah. Do you also have, let's say, external experimentalists who come and say, oh, we want to grow this type of material. Can you check out what to expect? Or let's say we want to compare epitaxial growth versus chemical vapor deposition. And then they say, can you estimate what type of quality we would get if you compare both?
We do. Unfortunately, I swept some of this under the rug. I didn't discuss the difficulties. For many of their requests, we're not quite there yet. And the reason is this, there's a subtlety. So these calculations are using plane waves, ab initio pseudopotential plane waves. The reason we use plane waves is because the plane waves have a large cutoff. It's like, it doesn't have a finite basis error. It turns out if you're trying to compute a derivative, a gradient on the energy, which is the force on an atom, if you have incomplete basis set, there's a term, it makes an error because, you know, like in molecules, the basis set are tied to the atoms, right? So as the atoms move, the basis set moves with it. So you need the gradient of that to make sure your forces are accurate. And so that's known as a Poulet term in chemistry, but basically it's a finite basis error. With plane waves, the basis set is essentially complete. In other words, these are actual energies given that pseudopotential. So we could do these gradients very well. Now, the downside of this is with plane waves, like if you have transition metals, it's like 100,000 plane waves. It's a huge calculation. So we can't do it for very large systems. These are relatively simple systems we could do. And for the things that the experimentalists are interested in, typically they're more complicated than this. Otherwise, they would know the answer. So we're working to go to a local basis, but treating the finite basis error better. And that's, of course, it's not limited to QMC. It's a common problem with chemistry. It's just that most of their methods haven't been able to reach a large enough size. They don't really worry about it as much. But now I think these become forefront issues. So because of that, we want to do a smaller basis, somehow correct for it. But you need enough accuracy in the correction and so on to be like accurate to be able to tell experimentalists that the structure is stable. Now, the question you're asking, there's a different twist on it, which is if there are some ideas of the structure, we could of course just check that structure. That's easier, right? Than this. This is pretending to say, well, we don't know at all and drive us to the structure. So that's a harder calculation. So there are easier calculations we could do, but even the easier ones, typically the materials are very complicated, lots of large supercells. So we need to make this faster. And we are working on newer codes that are going to work on GPUs, with local bases. And that will speed this up a lot. Again, the difficulty there is to figure out for this force calculation, the complete basis set limit and how to get rid of it.
Okay, thanks.
I think we had a question online.
Yes, but first ask the others. They have clever questions and mine will be stupid.
Sorry, could you pause 1 second? We have a siren going on. Go ahead. Can you?
Yeah, just I would like to ask a stupid question so that first the others should ask and I will ask at the end.
There will be questions, but no question is stupid.
Yes, absolutely. Yeah.
Okay, then. So if I understood correctly, you are not doing the metropolis like sampling like in the ALF because it would lead to ergodicity problems, right?
The constrained part is not doing the metropolis. Yes.
But is the ergodicity problem the only problem, or?
Yes. If we could figure out the ergodicity problem, it would be really nice to kind of not have to deal with the branching stuff and back propagation for observables.
And so here comes the stupid question. I don't see what the issue is with ergodicity. I mean, also in ALF they said they need ergodicity. I understand that if you start Markov chain and it is not ergodic, you won't travel through all the configuration space. But why is it not possible to travel a part of it, then got stuck and start again from a new random configuration? And if you and then wait to thermalize, walk again. And if you start sufficiently large, again and again from random configurations, then at the end you travel through all the configuration space or not?
Yes. Well, I mean, this is why you guys, young people, are important. You come in and try to figure this out. But here's the difficulty as we saw it before. Okay, so remember the current way you have many walkers, and you walk. So you're doing ground state. So you want to, at any time, so this is, let me call this time. So at any time, you want the condition psi t by, let me do the constraint version. T n, so this is index n, and this is t, okay? You want this to be
yes
at every time step. So this is branching random walk. Now, in the Metropolis version, one would carry this path, and one would define a fixed length beta, carry this whole path, and then try to move these around. Right?
Yes.
Wiggle the path.
Yes.
So if you I don't know, typically we depends on how global you want the update, we go, right, left, we sweep this, right?
Yes. Yes.
So at some point, suppose we're here. When we sweep this, we go up. And every step, we could check that our current position satisfies this condition when we switch to the right. And then you keep going. You could, well, first of all, when you propose, you get here, you realize the next moves are all stuck. They all go to 0. So suppose you go all the way here, and then you realize the next moves tau. And this tau has a sense of direction, whether it's coming from the right or left, right? But suppose now we're going this way. And this cannot be realized anymore, right? That you've just driven your path towards 0, and there's nothing you could do anymore. So imagine like an icing field, plus minus both lead to 0, negative. Then this path is terminated. You don't know, you have to come back and redo it. Right?
And why is it not possible to start here from a new path? And is it
you could, so you would start from a new path and do the same thing. But so this is one problem. You could go over, suppose you succeeded in all the way up here, right? You've done it, they're all positive. Now, if you go back, because you're going to make a measurement here.
Yes.
If you go back, you look at this way, you realize, oh, this actually, the wave function that's propagated from here by these paths violates the condition.
Yeah.
Which condition?
This coming this way violates the constraint, right? Because the idea is that you produce 2 wave functions Now, this second problem is less severe because in constrained path, we do a back propagation. In principle, we're not implementing that condition rigorously either. We're implementing a reverse condition. That's why it's not variational, the energy. But it does happen, right? When you carry a long path, this is going to happen a lot too. So you can restart a path, but basically when this is long, you restart a path by the picture that I showed yesterday, which went this way, I guess. You start from somewhere, you sample, you're guaranteed to hit a zero if you make this long enough, right? So in other words, this process, if you make this long enough, you're always going to hit something.
So that's the problem.
So you have to restart all the time.
Too frequently. Okay.
Yeah.
Thank you.
But
Thank you.
this is not to say it's obviously not a proof. And I think it's an interesting direction to keep thinking about it. Maybe with some of the Hamiltonian Monte Carlo, with some of the searches, one could do this more effectively. But I think one has to build in this knowledge somehow that you want to guide your thing in that direction. And then once you have a path picked out, you could do Metropolis. It's much cleaner. Then you could do all your measurements and all the machinery we know and love can be reactivated. So it's not a preference to break this and do this open-ended thing. But that's the reason that there's this ergodicity problem, which seems like it's intrinsic and its skating is sort of, that part is guaranteed, right?
And do I understand right that if one could solve this Metropolis-like sampling, then there would not be any further approximation in the sense that no mean field, like it would become exact?
No, there will still be. So at least the version I described is just a Metropolis version of realizing the same constraint. You should be getting identical answers to what I'm getting, but you would have, the sampling would be nice, right? You could, yeah.
You would have a variation of it.
You would, that's right.
That would
So
be something really
if you
right?
do condition 1 and condition 2, when you come back, you would have a better answer because your energy estimate would be variational, which this branching thing is not. That's an important point, yeah.
I also heard a sub-question in the question asked just recently, which I would like to address. So if you think about ergodicity problem and you just restart the simulation and you hope that you find another region, this doesn't really solve the ergodicity, because if you think about, let's say, the configuration space splits into two regions, for simplicity only two, and you have region A and you have region B, but the Metropolis can't get through them. Then if you restart, sometimes you will end up in A, sometimes you might end up in B, but it will be extremely hard to balance the percentage how you ended up in A and how you ended up in B according to the weight. So simply restarting and hoping that with an ergodicity you end up in a different part of configuration space is not really solving the ergodicity problem.
No, I agree. I would maybe push back a little bit. If this was that problem, if we have like a couple of domains, we just get stuck, then I would be really, I would say let's push that, because yes, it's true that if you do this, you have to distinguish the relative weight. But maybe then having some ingredients, you have multiple Metropolis paths and have some of the ingredients of the branching thing in there, as in weights. You keep track of some weights and you let them sort of fight it out, right? But then you still have the nice structure of the Metropolis path for each of them. I think if you have a simple ergodicity problem, like it's cut up in two domains, I think this is very much worth thinking about. No, this thing is not quite that, right? It just gets stuck always, right?
No, I didn't want to say that this is the kind of ergodicity problem. I just wanted to say that simply restarting the simulation does not fix the problem. You would have to be a little bit smarter about this to balance the relative weight of those two regions.
Yes, so exactly. The one advantage of these branching random walks, they have their disadvantages, is that even if, so this overcomes this ergodicity problem, but in other situations of ergodicity, it's easier for them because it's effectively like you have a complicated landscape. You can launch sort of detections, water streams from different places, and you let them fight out, right? So if you your single stream can get stuck in a local minimum, but there's some global balancing. You can still find it. So this is one advantage where, for example, when we actually do mean field calculations, right? Typically you get stuck in a local minimum. We actually do this. We launch a lot of them with relative weights. We do some annealing and it helps to find the global minimum. So that's one nice thing about the branching is that there's a global balance. It fights it out.
When you do this sequential in time sampling and you don't do the reverse, does this break detailed balance? And is it restored if you do the reversing?
It doesn't have a problem with detailed balance because detailed balance is not like the integral equation I was writing. You don't need detailed balance to correctly simulate the integral equation, right? So this correctly simulates the probability that you set out to simulate. Now, there is I think you also, Peter, alluding to a second problem, which is a problem, which is we go in this direction. Suppose we want to we measure the energy anytime because of the mixed estimator being exact, right? If we have the ground state wave function, I don't know if people know what I'm talking about I didn't talk about how we would measure, but as we go this in time, we have psi of tau, and we just need psi of t, h. This is equal to E0 if psi of tau is equal to psi of 0. You could use any trial wave function to measure because it's not eigenstate, it's correct. So this is called a mixed estimator. So for any observable that commutes with the Hamiltonian, you could measure it this way. But if not, you need some observable. You need a full estimator. Then what we do is we go forward for a while, and then we take the trial wave function, we propagate this back along the path. It's like trying to produce two sides. So this would be exact if we didn't have a constraint. It's effective. You can't back propagate for too long because branching, eventually you have a ancestry link problem. If you waited long enough, every child will have come from the same parent, right? So you decorrelate. You develop correlations. But this is exact if we don't have the constraint. If we have the constraint imposed going forward, this is what Thacker was alluding to earlier. Then when we go back, we're actually getting a wave function. This wave function is actually not equal to psi 0 bar, which is the constraint version of the exact wave function, but rather it's like that. It's a condition imposed in the reverse direction. What we're seeing is that this, for observables, sometimes is a little worse than if we could evaluate the variational estimator, psi 0 bar, which is the constraint version of the ground state wave function, O psi 0 bar. This is typically very good if you could compute it. But rather we evaluate versus psi 0 bar tilde O psi 0 bar. This is the reason that we're not variational, and often this result, when your constraint is severe, is not as good. But that's the few cases where we could find a trick to compute this. For example, in the superconductivity work, we computed this by doing a linear response, by making a Hamiltonian that's h plus lambda to compute it. So that becomes correct. It's a finite difference, or it's a linear response.
We really simulate the h plus lambda O.
Yes.
And then you derive.
We simulate this. It has two, for the superconductivity work, it has two advantages because this allows us to compute an order parameter versus a correlation function, which is very small.
That thing is like a pinning field.
Yeah, but global pinning field.
Yeah.
You apply an inducing field
and you reduce it basically.
Yeah. Other questions?
Okay, seems no more. And then we end the session and let's finish it again and we